Okay. Good. So let's remember where we are. Last class, we sort of took a little bit of a pivot. Up until last class, we had been designing algorithms that sort of single agents might consider running in some interaction in a game, either against other players or maybe a game against an adversary. We designed algorithms that individual players could use to make decisions in their interaction that would promise them various attractive guarantees, like regret guarantees of various sorts. And we started with simple regret guarantees, external regret guarantees, and we worked our way up to more complicated ones, things like swap regret and adaptive regret and stuff like that. And then last class, we were like, okay, we've got all of these complicated algorithms that people could run maybe and get these guarantees, but it's possible that lots of people in some interaction will just sort of not be sophisticated enough to run these complicated algorithms. You know, you get into your car, you're not firing up your laptop and playing follow the perturbed leader to figure out where to drive. You just kind of like type into Google Maps where you want to go. You get a prediction of what the traffic is going to be, and you just kind of like best respond to that. You follow Google Maps' suggestion of what you should do. And right, so the question we asked last time is, if we are in the presence of agents like this who are maybe sophisticated enough to best respond to some prediction about the state of the world, but maybe aren't going to be running something like follow the perturbed leader or these more complicated multi-objective optimization algorithms themselves, can we just produce predictions of the state of the world that have the property that for not just one agent, but maybe for any downstream agent whose utility function satisfies various mild regularity conditions, like it's Lipschitz and it's linear in the state, any such downstream decision maker should sort of simultaneously enjoy regret guarantee. Okay, and actually we saw like a really simple algorithm to do this last time. It just adds noise to the empirical history of the state so far and publishes that. And it had this property that sort of any downstream agent, if they just best respond to this sort of noisy history, will have no regret. Okay, no regret in sort of the simplest form we've studied, no external regret. And the reason was actually extremely simple. I mean, essentially, if you find yourself best responding to noisy forecasts, then you think you're just playing best response, but like really you're playing follow the perturbed leader. Okay, there were some slight technical differences between follow the perturbed leader, which adds noise to your utilities, calculated in some historical sequence, and what we did last class, which adds noise to the state. But we sort of showed that those differences didn't really matter, and you can sort of trick people into playing follow the perturbed leader, and so they didn't need to like do it themselves. They just think they're best responding, but they get these no regret guarantees. Okay, so pretty good. Where might we want to go from there? Well, there's at least two reasons you might complain about the result we saw last time. Maybe the simplest one is just that no external regret at this point is sort of the weakest form of regret we've seen so far in this class. It's what we started with in this class in the first couple of lectures, but over the course of the semester, we built up this machinery to get these much stronger forms of regret, things like swap regret, adaptive regret, subsequence regret, things like that. And so the first question you might ask is, okay, like, can we make predictions so that if people best respond to them, you get these stronger kinds of regret? But the other thing you might ask is, you might say, okay, well, maybe these decision makers, even though I sort of motivated them as being not sophisticated enough to run their own no regret algorithms, maybe they're not that naive, right? Like maybe they're not going to like best respond to our predictions if we don't give them a good reason to. And we haven't given them a good reason to. I mean, we've said, okay, if you do, you'll have no regret, but we haven't promised them that it is in any sense, an optimal strategy, of our, not an optimal strategy to take our predictions and best respond to them as if they are correct. Right? It might be that if you think a little bit harder, you could figure out better policies mapping predictions to actions that that would improve your utility, right? Like, why are we assuming that people are going to just do what we say? We might have to give them a good reason to do what we say, right? Like in sort of a mechanism design setting, we would not just assume that people are going to act as we would like them to act in the mechanism. We'd like to design the mechanism so that it is, for example, a dominant strategy in the game for them to act as we would like them to act. And so far, we haven't touched on that at all. We've said, if people best respond to our predictions, then they will have no regret. But we have not said anything about what their incentives might be to best respond to our predictions. And so you might worry that they correctly try to game the system in some way, not best respond to our predictions. And maybe in aggregate, they end up not having regret guarantees. Okay, so these are sort of two things that you might sort of complain about in, at least about last lecture in isolation. Okay, so does that story make sense so far? Like, everyone remember what we did last lecture, and then also understand the form of these two complaints we might level at it? Okay. So what I want to do over the next several lectures is figure out how to address these complaints. And towards doing that, I want to introduce a new online prediction problem that at first will seem like a digression, like we won't be talking about actions at all. We won't be talking about regret. We won't be talking about any of the things we just talked about. We'll just be sort of talking about sort of a statistical prediction problem where we want to predict some vector valued outcome in a way that has low bias in various ways. Okay, so that's sort of most of what I'm going to do today. I'm going to talk about this other problem that seems, or at least won't be, like immediately connected to the story that I just tried to motivate or to last lecture, but this will turn out to be an important tool in our ability to address these shortcomings of last lecture. Okay, so that's sort of the game plan for today. Okay, so let me call this problem adversarial prediction. And it's going to be a game against an adversary, much like the sort we've seen so far, but we'll see that the objective is a little bit different. Okay, so we're going to fix a bounded convex prediction space that I'll call C, and let's say that this is a subset of d-dimensional vectors that I'll normalize that they're bounded between 0 and 1. Okay. We'll also fix a context space X. Okay, intuitively, C is the space of things that we're trying to predict, and X is the information we might have available at test time before we make our predictions. Okay, so maybe we're trying to predict a probability distribution, like a distribution over d distinct outcomes. And maybe it's like some weather forecast, and we have some meteorological observations before we have to make the weather prediction. That would be X. Okay. So this is going to be a game against an adversary. What's going to happen is in rounds from 1 to capital T, first the learner observes some context. The learner observes context xt, okay, chosen by the adversary. Then the learner chooses a distribution over predictions. Okay, so this is a distribution PT over the prediction space. Okay, so just to sort of flag what might be a confusing thing coming up, a natural prediction space might be the set of distributions over some collection of events, right? Like the thing I predict might itself be a distribution, but the learner, the predictor here is also allowed to be randomized. And so if what we're predicting is a distribution, the thing they are selecting here is a distribution over distributions, right? Like the thing you're predicting is a distribution, but you're a randomized predictor. And so the thing, the thing you're choosing at this step might be a distribution over distributions. Okay. The adversary, knowing everything that's happened previously, chooses an outcome. Also, an element of C. Okay, and then the instantaneous expected bias of the learner's predictions is what I will call BT of L, the bias of the learner at round T. It's the expectation of a prediction drawn from the learner's predictive distribution of the difference between the prediction and the outcome. Okay, and the outcome is fixed. The only thing that's random is the prediction. So this is really just the expectation of the prediction, the mean of the predictive distribution, minus the outcome. Okay, so very similar kind of game to what we've studied throughout this class. Iterative game against an adaptive adversary, except the goal here is not to minimize cost or anything. The goal is to, well, we'll be more precise about different ways in which we can measure the performance of the learner here, which will give more insight into what the goal is. But as you can already sort of guess from what I've written down here, the goal is just to make correct in the sense of unbiased predictions. Okay, so we're not minimizing cost or whatever. We just want that in expectation, the thing we predict should be the thing that actually happens. Okay, this is a vector valued quantity, by the way. Like the state and the outcome are vectors. Okay, so maybe just to give some kinds of examples of what might be reasonable outcome spaces here. Right, so yeah, so we might be predicting a distribution over disjoint events, for example, right? Maybe it's gonna rain today, or gonna be sunny, or gonna snow, or gonna, there's a volcano will rise up out of the earth. Okay, like, And what we're going to do is predict a distribution over these D events. Maybe what the adversary is going to do is choose a realization of one of these events, which is also a vector in this space. It's just a distribution that happens to put weight 1 on one of the events. And what we'd like is that our predictions should be sort of unbiased with respect to the outcome. Okay, but we don't have to predict distributions. Maybe what's happening is we've got some downstream learner who's choosing which of k actions they should take. Okay, maybe the payoff for each of their actions is a number between 0 and 1. What we're doing is we're predicting the payoff for each of their outcomes. Okay, the payoff for each of their actions. We're predicting maybe a k-dimensional vector whose entries are just arbitrary numbers between 0 and 1. Okay, not a distribution. Then like they're playing in their own game, maybe some online linear optimization game. Eventually, their adversary chooses a cost function which realizes the costs for their actions. We want that our predictions for their actions should be unbiased with respect to their actual costs for their actions. Similarly, we might, in like an online shortest path kind of setting, might be predicting the congestion on different roads, maybe subject to some feasibility constraints, right? Like C is just a convex set, so it could be congestions, the set of all road congestions that satisfy flow constraints, for example. Okay, so maybe we want to predict like road congestion subject to some feasibility constraints. Some of them are actually going to be realized. Again, our goal here is sort of to be unbiased. Okay, does that make sense? Ira, you look puzzled. That's right. Yeah, so maybe like what you're puzzled about is that like if your hope was to make like this thing small, maybe you're observing that this is like plainly impossible because there is no, like, what does it mean to make unbiased predictions? There's no distribution that we've learned about that we're predicting. The adversary, at the moment that they choose this, right, knows the distribution we've picked, and so knows in particular the expectation of that distribution, and they're free to choose at this point a different vector which is not equal to the expectation of that distribution and just force us to have high bias. And so, if our goal was to somehow play so that this was always 0 or something, that would be plainly impossible. Yeah. So that's like maybe a useful observation that like you can't make this 0. Like what are we talking about? Like you go first, commit to the mean vector you're predicting, then the adversary goes, commits to the thing that you were trying to predict. If they want, they could pick it to be different than the thing you predicted. And so your bias isn't going to be 0, right? Like, in fact, even using the word bias is a little funny here. The expectation is over your own prediction, but you're predicting like a worst case adversarial vector. Okay, so this like might start to worry you. Hopefully not unduly. Other questions? Yeah, it's just like, hanging around for now. But as we start, so like, okay, so like this is related to what our goals are going to be. Plainly, the goal cannot be that our sort of instantaneous expected bias is 0 at every round. So we're going to have to ask that our bias is low in some aggregate sense. Okay, maybe this will bring to mind the sort of multi-objective kinds of optimizations we've been doing. And in like a weather prediction setting, for example, you might like that your bias is low conditional on, things about the cloud cover or the, barometer readings or whatever, right? Like hopefully you're using the information available to you to make good predictions. And so as we start to define more refined goals of what we want, we're going to Yeah, like we're going to basically ask for low bias on subsequences that might depend on the context. Good. Other questions? Okay. Good. So we noticed already that, like, we can't hope that the instantaneous expected bias every day is 0 or even low. So that's the only thing that matters for the instantaneous bias. If our goal was to make this 0, we wouldn't need to worry about that. So in part because it's just a losing game no matter what. But it will matter for the more refined goals we write down informally, because what we're going to do is we're going to ask for low bias on various subsequences, and the subsequences can depend on our predictions. And the adversary, in trying to make our aggregate bias on different subsequences high, like the instantaneous bias only depends on the mean, but which subsequence it belongs to can depend on the realization. That's going to be the reason. Good. Other questions? Okay. So asking for sort of every day the bias to be small, that's too hard. Let's go the other way and ask for something that's too easy. Okay. So maybe like by analogy to like our study of regret. The first kind of regret guarantees we asked for were just that our regret was low over the whole subsequence. This is sort of like a marginal guarantee. Even that wasn't like trivial. We had to like design algorithms like multiplicative weights and gradient descent to do it. And then we went on and asked for sort of harder guarantees that asked for regret on different subsequences. So I'm gonna sort of go through the same kind of collection of maneuvers here. First, I'm gonna ask for just low marginal bias that sort of on average over all of the predictions, the average of your prediction should equal the average of the outcome. We'll find that actually here, that's sort of so easy so as to be trivial. Like the algorithm to do that will be really stupid. And as we'll see, it's not going to be a useful thing to do. Okay, so marginal guarantees, like marginal guarantees were still interesting in the regret setting. They're sort of not interesting here. They're too easy here. But we're going to strengthen them in the same way we did regret and ask for conditional guarantees of various sorts. Okay, so let's do the too easy thing. Well, first of all, what is marginal bias? So pick the transcript. The learner's marginal bias after T rounds is, I'll write it as the bias of the transcript. And it's just going to be the L infinity norm of the average of our predictions minus the average of the outcomes. Okay, so we're taking our instantaneous bias, okay, which is, remember, a vector valued thing. But we're not, like the goal is not to make that small every day. We sort of noticed that might be impossible. So instead, we're going to sum up our instantaneous bias over all of the rounds. This is a vector. This is a d-dimensional vector. And we're going to ask that the L infinity norm of this vector be small, which is just asking that every coordinate of this aggregate vector should be small. Okay. Okay, so like impossible to make the sort of per round bias small, but maybe now that you've seen all of this multi-objective optimization stuff, you should sort of have some intuition that making the aggregate small might still be possible, right? Like, the adversary might be able to force us to have some high value in each coordinate or in some coordinate of our loss every day, but maybe we can arrange things so that it is a different coordinate every day in which we have bias, and maybe the bias has opposite signs or something, so that we can hopefully arrange for things to cancel out over time. Okay, so this is just asking that on average over time, our predictions should equal the outcome. And this is maybe looking more like what we typically mean by sort of statistical bias. If we have a predictor that has low statistical bias, that doesn't mean it's right every day. It doesn't mean that it's perfectly accurate. It means that it doesn't have any systematic proclivity to over or underestimate. On average, over all of the examples, our predictions average out to the actual outcome. Okay, so this is literally sort of the maximum statistical bias in the coordinate on the empirical distribution where we just pick a day, little t, uniformly at random. Okay, good. Okay. Can anyone give me an idea for a really good algorithm for guaranteeing low statistical bias in the adversarial setting? Suppose you're trying to figure out what to, you're like a sort of do-it-yourself weatherman. You are just trying to figure out, like, if you wear a sweater out every day, but you're too lazy to check the weather forecast. What's a pretty good algorithm you could use? Yeah, it's predict what happened yesterday. Why go to meteorological school? Okay, so here's an algorithm that's going to have great marginal bias in this problem, even against an adversary. Okay. So on each day t, what we're going to do is we're going to observe the context. Okay, we're going to, go and climb up on our roof and look at our weather vane. We're going to break out our barometer. We're going to check pressure readings. We're going to examine all of the satellite data we've got. But we don't know what any of that stuff means, so we're just going to ignore it. And then we're going to predict that today's outcome is going to be equal to yesterday's outcome. And then, we get to observe today's outcome. Okay, and we continue. I'm just going to predict that what's going to happen today is what happened yesterday. Okay. This is, in some sense, according to maybe the metric we've laid out, like a great algorithm. It's got really low bias. This algorithm guarantees that for any sequence of outcomes, could be chosen by an adversary, that the transcript that will be generated will satisfy that its bias, which is just, after all, the L infinity norm of the sum of the differences between our predictions and the outcomes, is at most 1. Doesn't even grow with t. It never goes above 1. Okay, no dependence on t at all. Best bound we could possibly hope for. Can anyone tell me how come? Everything cancels out, right? We're like looking at like the average of our predictions versus the average of the outcomes. Well, our predictions are equal to the outcomes. They're just off by 1. So there's only one forecast, actually the last one, that doesn't cancel out, that isn't, and so that's all we pay for. So like the proof, super simple. For any coordinate I, if we look at the sum of the difference between coordinate I of our prediction and coordinate I of the outcome, well, what's our prediction? It's just yesterday's outcome. And so, we can sum these two things separately. The outcome is just the sum over all of the days of the realized outcome. Oops. And our prediction, since they're just yesterday's outcome, we can think about that as the sum over all of the days, not up until day t, up until day t minus 1. We never predict day t. That's what we would have predicted at day t plus 1, which never happened, of the outcome. And so this is just coordinate I of our prediction, or coordinate I of the outcome at the final day, which, since the outcome space has coordinates bounded between 0 and 1, is bounded by 1. Okay, so like the unnormalized bias never goes above 1. If we, we might have reasonably looked at the normalized bias, the average of these things, 1 over t. This would say that our bias goes to 0 at a super fast rate, at a rate of 1 over t. Okay. Okay, so given how stupid the algorithm is, this might lead you to be sort of unimpressed by the goal we set out for ourselves. And there's another way to sort of maybe see that asking for low bias of this sort is not actually very interesting. One is just by seeing how you can do it, but okay, that's not fair. You shouldn't convince yourself that a problem is dumb only after you see that it has an easy solution. Maybe you should convince yourself that a problem is dumb because it's not useful, right? So let's sort of go back to the story from the beginning of class, on last class, like, what are we trying to build up machinery to do? It's to give a way to make predictions so that downstream agents, if they act on those predictions, will have good guarantees. Okay, so suppose that what we are doing is predicting the cost for some downstream learner who's got different actions. Okay, and suppose we decide, okay, like, let's just try to predict costs so that we have low bias. Okay, we could do it this way or some other way. Well, actually, maybe we're going to do it this way. And let's sort of see that this is not going to be able to guarantee that the learner has low regret. They might have actually maximal regret. Okay, and the example is maybe the same example that we used to see that be the leader was not a no regret algorithm. Or sorry, follow the leader was not a no regret algorithm. Okay, so remember, how come we had to run follow the perturbed leader? How come follow the leader was not a no regret algorithm? It was because you could have this sort of alternating sequence where you were like always doing the wrong thing. Okay, so let's sort of remember what that sequence might have looked like. It's just you've got two actions. Initially, the cost for action 1 is 1. The cost for action 2 is 0. And it just alternates. 1, 0, 0, 1, 1, 0, etc. Okay. In this setting, either action is the best fixed action. Either action will give you a cost of 1 half of the time. So your cumulative cost will be t over 2, playing any fixed action. But if what I'm doing is predicting today's cost vector by just saying it's going to be yesterday's cost vector, even though, as we've seen, I'll have an impeccable bias bound. It will cause a learner who is best responding, who is choosing their action as if my prediction is correct, to have a terrible regret bound, right? Because if the learner always thinks that today's cost vector is yesterday's cost vector, they're always going to play exactly the wrong action, right? In this sequence, the action you should play changes every day. And so if you're playing one day off, you're getting cost of 1 every single day, and you have maximum regret. Okay, regret like t over 2. Okay, so bounding marginal bias, sort of unlike bounding marginal regret, that's not interesting, both because it's not useful for downstream decision making, and relatedly, it can be done sort of without any doing anything useful, just predicting what you did yesterday. Yeah. If I predicted the average of what's happened so far, that would be a little bit better, but also wouldn't give a no regret algorithm, or wouldn't give downstream learners no regret. That would cause them to follow the leader, which would break on this very same sequence. Right. Then you can add noise. Yeah. So you can yeah, that's right. There are other simple algorithms like the one we saw last week that do have nice regret properties. That will maybe still have low bias. To think about that. Is it like totally obvious? Yeah. But but my point is not that useful algorithms will have high bias in this way. In fact, the algorithms we're about to see won't. They will have low bias. My point is just that this objective on its own is not enough for the kinds of guarantees we want. We're going to have a more sophisticated objective. Okay. Okay, nevertheless, like despite the fact that our initial investigations of statistical bias don't make it sound like a super interesting quantity to control, I want to plow ahead and sort of start asking for refinements of this goal in the same way that we asked for refinements of the regret guarantee. In particular, like what did we do? Like marginal regret was already interesting, but we asked for stronger forms of it that basically wanted our regret to be 0, not just overall, but conditional on various events, conditional on being members of various subsequences, for example. Okay, so that's the way I'm going to proceed here as well. I'm going to think, okay, like, what if I don't just ask for low bias marginally? What if I ask for low bias subject to various conditioning events? Okay, so let's say in a very similar way to how we talked about subsequences in the regret setting, let's talk about events in that same way. So let's say that an event E is defined by a subsequent selection function I'll also write as E, which maps, let's say, the current time step, or maybe the transcript up until now. It's okay if it depends on history. And the prediction that we make could depend on the prediction that we make. And any available context, the event could depend on our barometer readings. Maps all of that to a number between 0 and 1. If you want to think about it as mapping to a binary number, 0 or 1, you can think of it as saying the event occurred or it did not occur, but it's going to be fine if it maps to a number, like a weight between 0 and 1. Given a transcript, the bias with respect to event E will be same as before. We're going to sum up over some subsequence of our predictions and subtract off the outcomes, and that's going to give us a vector. And we're going to want that all of the coordinates of that vector should be small. The L infinity norm of that vector should be small. Okay, and what are we sort of summing up over? Well, it'll be the expectation over our predictions at that round of now this subsequent selection function corresponding to the event times the per round bias. Okay, so if you think about, this is some weighted sum in general, or if you think about this as sort of outputting numbers that are either 0 or 1, it's selecting days. We're summing up only over those days, which can depend on the context, the history, and our prediction, only over those days for which this event E was active. And we're looking at our marginal bias on that subsequence of days. Okay, so the difference between our predictions and the outcomes, not just marginally now, but on some particular subsequence. Okay, and again, like it'll be most interesting to ask for this not just for one subsequence, but for like a collection of subsequences. They might intersect. And so for a collection of events script E, a transcript IT has script E bias bounded by alpha if the max over all of the events in our collection of the bias of our transcript conditional on that event is at most alpha. Okay, so yeah. That's right. So good. So let's think about the timing, because the events can depend on your own prediction, but they cannot depend on the outcome. So at the moment when you realize your prediction, you know whether the event will be active today, because you know what day it is today, you know what the barometer readings were today, and you've just realized your prediction. Of course, when you're deciding what to predict, you don't know which events will be active. You control that, but it's not fixed, right? So these are not in general going to be like what we called before, like action-independent subsequences. They might depend on your own prediction, but you're not going to be surprised by it. At the time you realize your prediction, you know all of the events. Yes. So what's the proposal? Yes. So it's good. So I sort of said, okay, this isn't interesting because we can achieve it in, a dumb way. So now you're asking the very good question: can we like achieve the stronger thing in a dumb way? Remember the last page. I think you're imagining that there's only one event active each day. When you say the event, the last day when the event was active, we have a lot of events. Different ones were active on different subsets of days. That's true. So that's true, although maybe like a different observation. So like, just as with regret, it's not going to be possible to get sort of non-trivial subsequence bias on sort of events or subsequences that trigger only once, for exactly the reason you just said, like, because then it's just asking for per round bias. Separately, you might say, okay, maybe I care about a collection of subsequences that trigger enough times so that there's some hope. Why can't I just sort of say, okay, I'm going to like basically run a copy of this for each subsequence, which is, I think, the core of your proposal. You could do that if the subsequences were disjoint. If it was, like, cloudy days and not cloudy days, I'm like, all right, like, here's what happened last time it was cloudy, or here's what happened last time it wasn't cloudy. Then I could just repeat this analysis on each subsequence. Maybe if I was looking at my marginal bias, maybe I'd pay something linear in the number of subsequences or something. Okay, but it won't work because, in general, the events are not disjoint. So like there might be like 6 events. Well, there's a couple things. So they're not disjoint. Second, because the events depend on what I play, I can't say that I'm going to just predict whatever happened last time this event was active, because it might be that the thing that happened last time this event was active causes the event not to be active today. So I think those are 2 different problems. So one, the subsequences are not disjoint. Second, even if they were disjoint, the events depend on what you play, and so there would sort of be a self-referential problem that would arise if you tried to like run this separately on each subsequence. Yeah, so I think both of those things happen. Yeah. You're saying why don't we just ask that our bias, like our daily bias, be small pointwise? No, well, yeah. Well, I guess that's too hard. But yeah, I mean, like you're right that if we just like if we just sort of said, okay, I just want this to be small every day, forget this aggregation bullshit, then that would be a stronger thing. But there's no distribution. We're predicting against an adversary. And so that's hopeless because the adversary gets to choose what happens only after we commit to our expectation. So we need to settle for something that aggregates over something, a guarantee that aggregates over something. Aggregating over everything, too weak. Now we're sort of attempting to define a more refined guarantee that's going to simultaneously aggregate over a bunch of different subsequences. TBD whether this is useful for anything, but our hope is that if we can figure out how to do this, then there will be some way of cleverly choosing these events so that our predictions will, in fact, be useful for downstream decision makers of various types. That's sort of the game plan here. Does that make sense? Okay, but we haven't gotten to that second part yet. We're just sort of thinking about this sort of conditional bias kind of guarantee. Okay, does everything make sense? Okay, so we've got some stronger benchmark now. We don't know how to, adopt our sort of silly algorithm to achieve it for the reasons we've discussed, which is good because I sort of complained about this marginal guarantee by appealing to the silliness of this algorithm. Let's think about like how to solve this though, right? Like at this point, we have built up the machinery to be able to solve things like this, right? Like you should be like thinking now about the kinds of multi-objective optimization tools we've developed in this class, right? Like, we can phrase this as a multi-objective optimization problem, right? What are our objectives? Well, like there's one for every coordinate of our prediction and for every event. And in that coordinate and our event, we would like the sum of our predictions to be not too much larger than the sum of the outcomes in that coordinate. And also we'd like it to be not too much smaller. Okay, so we can sort of imagine encoding a multi-objective optimization problem where we enforce that the bias is small by having one objective coordinate for every coordinate of the vector we're predicting. And for every event that we want low bias on, and for every sign, we don't want the bias to be too positive, and we don't want the bias to be too negative. Okay, so that's 2DE coordinates, 2DE coordinates. Okay, 2DE different objectives that we sort of want to simultaneously satisfy. Okay, no big deal though, we know how to handle multiple objectives. Okay. So let's, start remembering the kinds of things we would need in order to encode this low bias prediction problem as one of these multi-objective optimization games that we've developed the machinery for solving. And if we remember, one of the sort of technical things we needed was that both players should have a convex strategy space, and that we have these like loss functions for each objective value, and they need to be convex in the minimization player's actions and concave in the maximization player's actions. Now, if you sort of look at what this, if you're sort of imagining that the cost functions are probably going to kind of look like this bias term here, and maybe the learner is going to play predictions and the adversary is going to play realizations, maybe you sort of say, okay, well, everything looks kind of linear in the adversary's actions, so that's good. Linear is convex and concave. And, here things look linear in the learner's actions as well, but the learner's actions also show up in triggering these events. And the events could be complicated because we didn't assume anything about them, right? Like they don't have to be even continuous functions, forget, convex and concave. So, okay, so we're going to need to be a little bit careful about what the learner's strategy space is. Okay, in particular, we're going to solve that problem the way we always solve it, which is allowing them to randomize. Okay, but randomize over what? Okay, so like the learner has some like continuous strategy space, right? It's like this prediction space C. Distributions over a continuous strategy space, those are going to be complicated objects. So our plan is going to be to like discretize the strategy space so that the learner only has maybe a lot, but only finitely many predictions, and then define their real strategy space to be distributions over these finitely many predictions. Okay. Let's say that a set C epsilon, which is a subset of the prediction space C, which we remember is itself a subset of 0, 1 to the D. And I guess given how many times I'm writing this subset thing, it's too bad I called the variable C, but you guys get it, I guess. Let's say that this thing C epsilon is an L infinity epsilon net for C if for every vector S in the outcome space C, there's some other vector S prime in the epsilon net such that S and S prime are close in the L infinity distance, such that if I look at the maximum coordinate difference between S and S prime, it's less than epsilon. Okay, right, so like C is our continuous prediction space. It's got like a ton of vectors in it. We're gonna be working with a finite subset of C, okay, that is supposed to, capture most of what we can do with all of C. How does it capture it? Well, it's gonna have the property that no matter what vector you care to think about in C, I've got one in C epsilon that might not be equal to your vector, but is nearby. Nearby in the sense that coordinate-wise, it doesn't deviate by more than epsilon. Okay, and an observation, we can always take C epsilon to be something on the order of, at most, 1 over epsilon to the d, just by, right, like every coordinate's a number between 0 and 1, so we can just discretize every coordinate up to epsilon. There's 1 over epsilon values in every coordinate, and we can get an element of C epsilon by choosing one of those 1 over epsilon values for each of the d coordinates. Okay, so big set, exponential in the dimension, but finite. Because there's d coordinates. Why would it be d over epsilon? Yeah, how many vectors are there when you do that? Yeah, so you have 1 over epsilon choices you can make in each of the d coordinates. That's like 1 over epsilon times 1 over epsilon times. Okay, so it's 1 over epsilon to the d. It would be great if it were d over epsilon, but unfortunately no. Okay. All right, so we can talk about finite subsets that are like close to, that sort of cover our prediction space in like L infinity normal. Okay, so let's think about how to encode the goal that we have low subsequence bias, low conditional bias, conditional on these events, as a multi-objective optimization game. Okay, so that we can just apply the machinery we developed in studying multi-objective optimization to study this, to solve this problem as well. This is going to be the encoding as multi-objective optimization. Okay, so we're given a prediction space C in d dimensions, a set of events E, and what we're going to construct is a 2 times d times number of events dimensional multi-objective optimization game. Okay. So remember, what do we need to specify such a game? We need to specify the strategy space for the learner, the strategy space for the adversary, and loss increments in each of our in each of the dimensions. And these things are going to need to satisfy various technical conditions that we'll have to verify. Okay. Okay, so the strategy space for the learner at every round is just going to be the set of probability distributions over an epsilon net of C. Okay, so remember, what were the requirements for the strategy space of the learner? It had to be a convex subset of some finite dimensional vector space. Well, the probability simplex is convex, the epsilon net is finite, and so we're good. Okay, we would have been in trouble if we tried writing the set of distributions over C, because now this wouldn't be a finite dimensional vector space. Okay, that we need to specify a strategy space for the adversary. We'll just set this to be C itself. C is already a d-dimensional convex set. Okay, the adversary doesn't need to randomize. And finally, what are our loss increments? Well, the claim is we're going to have 2 times d times e of them. Well, what are those? There's going to be 1 for every event on which we want to have low bias, 1 for each coordinate of this bias vector. We tried to control the L-infinity norm, so we want the bias to be small in each coordinate. And how about that too? Well, like absolute values are hard to deal with. So rather than having 1 objective that has absolute values, we'll have 2 objectives, one of which says the bias shouldn't be too positive, and another of which says the bias shouldn't be too negative. Okay, so for each event, for each coordinate, and for each sign, sigma, which is either going to be +1 or -1, we'll have a loss increment in that coordinate as a function of the strategy of the learner, which is a distribution over predictions, and a strategy of the adversary, which is an outcome. And it's just going to be defined to be sigma times the expectation over the draw of the prediction from the learner's distribution of the single round bias weighted by event E. The bias in coordinate I. Okay, so this thing is not a vector, it's a number, because we're indexing a particular coordinate, I. Okay. So does the encoding make sense? We need to verify, by the way, that this loss function is convex in the learner's action and concave in the adversary's action. But indeed, well, in the adversary's action, the objective is linear. Okay. And in the learner's action, well, if the learner's action had been S hat, we would have been in trouble, because then it would not be convex in the learner's action. That's why the learner's action is not S hat. The learner's action is PT, a distribution. And this is taken in expectation over that distribution. And so it is also linear in the learner's actions because expectations are linear. Okay, so the loss increment is actually because of our use of randomization. This is why we always use randomization, linear in both players' actions. Okay, so the requirements for our multi-objective optimization framework are satisfied. Okay. And this is just, just to like, why did we write this down, right? Like, what is going to be the cumulative sum of the loss increments? Well, if we sum up, if we take, a particular event and coordinate and sign, and then sum up over all of the days, this is just going to be the bias in that coordinate in that day signed by sigma, so either the positive bias or the negative bias. And so if this is small in every coordinate and every event and for every sign, it'll be that our overall bias is small. Okay, makes sense. Okay. SIT lives inside BT, which is of course C. So it's just an outcome. Good. Okay. Okay, so this is like a legitimate encoding in our multi-objective optimization framework. We've got algorithms that like generically solve multi-objective optimization problems. So let's see how well they do. And remember, like the key quantity to understand how well you can do in this multi-objective optimization framework is the adversary moves first value of the game we've defined. How well you could do in a single round of this game, not in aggregate, if the adversary first told you what they were going to do, and then you got to best respond, which is the opposite order of events. But the kinds of theorems we proved are that if you can do well in a single round of interaction, if the adversary moves first, then you can also do well in aggregate, summed over all of the rounds of interaction, even if you have to move first. Okay. The lemma is that in this encoding, the adversary moves first value of the game, which remember is just, well, how large the adversary can make the maximum coordinate value if they move first. So the maximum overall outcomes the adversary might choose of the minimum overall distributions that we might choose of the maximum over all of the coordinates of the loss function. And there's one indexed by each sign, each event, and each coordinate of the loss in that coordinate, given the chosen actions. The claim in this lemma is that the adversary moves first value of the game is pretty small. It's at most epsilon. Where what's epsilon? It's the discretization parameter in our epsilon map. Okay. Okay, well, what's the proof? Well, as in many of these arguments, like in general, right, it's sort of the beauty of these sort of minimax kind of arguments. In general, it might not be clear how well you can do in these games, but thinking of the adversary as moving first is often very clarifying because it's easy to predict something if you already know what it is. And so, like in this objective, you're sort of, if you just want it to equal 0, you're sort of trying to just match what the adversary plays, right? The adversary plays some vector, you're trying to be unbiased. You want to, like match what they do in every coordinate. If you could just copy their strategy, if they commit to S, if you could say, haha, I'm going to predict S, then you'd have 0 in every coordinate. You can't do that because the adversary is free to play any point in this outcome space. You are restricted to playing in this discrete set, but this discrete set is an epsilon net that covers the prediction space, and so you can't maybe match what the adversary is going to do exactly, but you can do it. You can match it up to epsilon in every coordinate, which is why the adversary move's first value is going to be epsilon. Okay, epsilon, by the way, was just a product of our own construction, so we could make this as small as we want. So this is sort of like saying the adversary move's first value can be made arbitrarily close to 0. Okay. Right. So let's just sort of define that. So given some action by the adversary, let's let P of S, an action by the learner, be a distribution that places all weight on some S prime T on some S prime in the epsilon net, such that S minus S prime, in every coordinate, the difference is at most epsilon. There is such an S prime because it's an epsilon net. Okay, so then the adversary moves first value of the game. Well, first they pick S, then we get to best respond. Well, our best response is only going to be better than playing P of S. P of S is something we got to do. Okay, so the adversary moves first value of the game is at most what it would be if we always played P of S when they play S. So it's at most the maximum over S of the maximum over all of the coordinates, sigma, E, and I, of the loss in that coordinate when we play P of S and they play S. Okay, because P of S is something, and we're comparing to the best thing we could play. And this is just, well, let's like unwrap what this loss increment is. It's sigma times the event indicator, given that we play action S prime, because P of S always plays S prime, of the difference between S prime in the ith coordinate and S in the ith coordinate. And, well, this is +1 or -1. I don't know which one. This is some number between 0 and 1. Okay, so far the product is some number between +1 and -1. And this difference, well, since we picked the closest point in an epsilon net, is somewhere between -epsilon and epsilon. We've got a number that's between -epsilon and epsilon multiplied by a number that's between -1 and 1. This whole thing is at most epsilon. Okay, the adversary moves first value. In this game, it's at most epsilon. Epsilon, by the way, a parameter in our construction. We can take it as close to 0 as we like. Okay, makes sense. Okay. So let's now turn the crank. We've taken this new problem of making low bias predictions. We've encoded it as a problem we know how to solve, multi-objective optimization. Okay, what happens when we use the algorithm that we have for solving multi-objective optimization on this encoding? Okay, so the theorem is if we run a multi-objective optimization algorithm on this encoding, what we have is that given given the transcript that will result, the E conditioned bias on that transcript will be at most epsilon times t, the number of days we run this prediction problem for, plus whatever our adversary moves first regret was on this transcript. Okay, that's the claim. And how come? Well, that's gonna just basically follow from expanding out the definitions. So remember, what is the adversary moves first regret? Well, it's the maximum over all of the coordinates of the loss increment in our multi-objective optimization game of the cumulative loss in that coordinate cumulative over all time minus the adversary moves first value of the game, right? Like adversary moves first regret bounds the cumulative loss in the maximum coordinate as a function of the adversary moves first value of the game. And we just bound the adversary moves first value of the game by epsilon, it's at most epsilon, which means that since we're subtracting off the adversary moves first value here, this is at least the cumulative loss in each of these coordinates minus epsilon times t, because we pay epsilon for the adversary moves first value in each of these t coordinates of the sum. And well, what are these loss functions? For a particular coordinate I and a particular event E, we're just summing up over the, well, sigma signed bias in that coordinate. And since we're gonna have a bound on all of them, right? A bound on the sigma signed bias for both sigma and minus sigma, we're really gonna have a bound on the absolute value of the loss. And since we have a bound on the absolute value of the loss in each coordinate, we're really going to have a bound on the L infinity norm of the vector valued bias. Okay, so this is just, like pulling out the maximum over the sign and turning that into an absolute value, and pulling out the maximum over the coordinate and turning that into an L infinity norm on the vector. What we're left with is the maximum just over the events of the L infinity norm of the sum over all of the rounds. Now just plugging in what our loss function is, the expected weight of the event indicator function times the difference between our prediction And the outcome, the L infinity norm of this, still minus epsilon t. Okay, which is just the definition of the E conditioned bias minus epsilon t. Okay, so we get bias bounded by the AMF regret of whatever algorithm we're able to use to solve this multi-objective optimization problem, plus, some additional epsilon t slack here because the adversary moved first value of the game. It wasn't 0. It was, like arbitrarily close to 0, but not quite there. Okay, makes sense? Okay. And so just, corollary of this, like remembering what kinds of AMF regret bounds we were able to get. Like there exists an algorithm that for any collection of events E and for any prediction space C, as long as it's d-dimensional and has, like outcomes bounded between 0 and 1, can guarantee that the bias on the resulting transcript, given the collection of events, is bounded by, okay, let's remember what our AMF regret bound looked like. It was 4 times the square root of t times the log of the number of, times the log of the dimension of our optimization problem. What's the dimension of our optimization problem? It's 2 times d times the number of events. So we pay for 2 times d times the number of events, only inside the log, plus epsilon t. And we can make the sort of epsilon t term go to 0. The epsilon t term we can make negligible because we can, set epsilon to be as small as we want. Okay, which means that although we just defined this problem today, we've already built up the machinery earlier in the class to solve it. Marginal bias, if we just wanted low marginal bias, we just predict what happens today is what happens yesterday. It's not very useful. But actually, you give me an arbitrary collection of events that can depend on the context, my own action, and the history. And I can promise you predictions that guarantee that the bias grows only with root t times the log of the number of events. So you can give me quite a few events and the bias will remain small on all of them. So that's pretty good. It's not clear yet, by the way, like why it's pretty good, like what it's useful for, but that's what we're gonna turn our attention to next time, right? Like we have now in our hands the ability, oh, by the way, flagging what will be an interesting problem, we have the ability if we assume we can run this algorithm, right? But in this game we've defined, the strategy space for the learner and the adversary, it's really big, right? Like the learner and the adversary are playing vector, like d-dimensional vectors. There's like exponentially many of those. In fact, the learner is playing distributions over d-dimensional vectors. So there's like doubly exponentially of many of those. And the algorithm that we're referring to in this theorem, what does it do? It solves a zero-sum game every round defined by these action spaces. But although in principle that's possible to do, you might worry that it's going to take you exponential time to do it. So I said there is an algorithm. I did not say there is an efficient algorithm, right? Like the bias bound we're getting is really good. It depends only logarithmically on the dimension. Okay, that's because the bounds we proved in the AMF regret setting depended logarithmically on the number of objective coordinates we had, but were entirely independent of the size of the action spaces. So like it was fine in terms of this bound that the action spaces were huge, but when implementing this algorithm, you might start to worry. Okay? So there's sort of maybe two things left unsaid at this point. One is we've got a way to get these really good bounds on bias, but it's not yet clear what these are going to be good for. Okay, so what we're going to start interrogating next class is, are there ways to choose events E so that making unbiased predictions is actually useful for something? And also we're going to have to worry about like, how would you implement this algorithm, right? There's a computational question of like, how do you solve the particular game we need to solve to implement this algorithm, which happens to have an exponentially large action space. Okay, so there's a computational question as well, but we'll be able to say things about both of those things. Say things about both of those things next time.